doing?
Hello, everybody. Welcome back. How is everyone? All right, doing good. That is good to hear. So, welcome to this data mining lecture on the lovely Monday night. Today, we are going to continue on our clustering lecture. Last time we talked about what? We talked about hierarchical clustering and we talked about k-means, right? So two very common, very popular clustering algorithms. And I hope you will be able to understand the goal of clustering, and you will be able then look at other clustering algorithms to help you process your data set, especially for your project. All right, so today we're going to continue on this topic, clustering, and we are going to discuss two algorithms. One is the BFR algorithm, and then we are going to talk about the QR algorithm. So QR algorithm, we are going to briefly talk about it. Mainly, we're going to focus on the BFR algorithm today. So the BFR algorithm is an extension of k-means to large data set. All right, so extension to k-means, that means basically we are going to use k-means. However, we are going to make k-means to be able to handle large data set. So before we look at the algorithm, what would be a problem of using large data set for k-means? Anybody? Why is large data set a problem? Well, think about k-means, right? So you decide on, remember our example, you decide on two classes, then you have to assign all the points to either cluster, right? So let's say these are all your points. your algorithm needs to be able to calculate all this pairwise distance between a point to a cluster center to another cluster center, then you can do the assignment, right? If you don't remember, that's here. You have lots of points. You decide on cluster center, you start to assign points to a cluster, points to another cluster, then you move the cluster center because all the cluster points has changed, and you have to update the center, then you have to update the assignments, and so on until it's stable. Okay, so think about this. If we are working on a large data set, what would be the problem? Does this still work? It's very time consuming, yes. So, but what's the computational expensive part? Well, first, you have to calculate the distance between a point to all the cluster centers, right? Second, if you have a really large data set, you might not be able to store all the data points in your memory. That means you have to read some data points, process it, and write it back to the disk and do the same thing again. And as you saw in our previous lectures, this is very time consuming. So we want everything to be able to process in the memory. Also, we do not want to read the entire data set multiple times. That's why we are going to talk about this BFR algorithm that will be able to help us do that. Okay. So the BFR algorithm is a variant of the k-means algorithm. And the goal of the BFR algorithm is to handle very large data sets. So here it says disk resident data set. This typically you have gigabytes of data or terabytes of data that you cannot read the entire data set into your main memory. So the BFR algorithm, because it's based on k-means, it can only deal with the Euclidean space. And the BFR algorithm also has its own assumption about the data set. It says the assumption is that clusters are normally distributed around a centroid in an Euclidean space. Okay, so if you're not familiar with the term normally distributed, it just looks like this. This is the probability density function of a normal distribution or a Gaussian distribution. Here is your mean, and the shape of the probability density function depends on your standard deviation in the data set. So for example, if we ask the question, what would be the probability of seeing a data point from this range? What is this range? Well, this is from the mean of your data set to one standard deviation away. This part is 68%. And based on a normal distribution, we know that 95% is 2 standard deviation away, 99.7% is 3 standard deviation away. So if you are not familiar with this, I'll just give you a very simple example. Say you have a data set and every data point, D, only has one value. So let's say this is column 0. Okay. And let's say this is for students. So this will be column 0 will be GPA. And let's say you collect 10,000 students. So D1 to D10,000. Each of the students will have a GPA value, right? And for example, 3.2, 3.1, and so on. And if we say this student GPA variable is normally distributed, that means we can fit a Gaussian function, Gaussian distribution function on top of this data set. And if you go look at the definition of Gaussian probability density function, it has two attributes, mu and sigma, which is the standard deviation. And I just put Gaussian probability density function. Okay, two parameters. So what would be the mu and what would be the standard deviation? This looks familiar, right? This looks very similar to what we have been talking about in our last lecture on AGM. You have a model that you would be able to describe your data. Okay, so your model has parameters, mu and standard deviation. And you also have your data. Remember our 1, 2, 3? 1, 2, and 3 is to estimate these two parameters using your data. And again, it's maximum likelihood estimate, but it's very simple. In this case, maximum likelihood estimate, the best Gaussian model that will be able to describe your data set with the highest likelihood would be the mu equal to the mean number of all the GPA here. And the standard deviation is the standard deviation of all the GPA here. Okay, cool. So let's say you do that and you figure out a mu, you figure out a sigma, you will have a curve like this. You have that function. And in this function, because here the mean is already 0, that means you take each of the GPA value, you subtract it by the mean number, so the mean will be 0. And when we model this as a Gaussian distribution, you know that most of the data points are within one standard deviation. So here's one, here's another one of the mean number here, and that's 68%. 95% is 2 standard deviation away. 99.7% is 3 standard deviation away. Okay, so that's the basic assumption of this BFR approach. If you are not familiar with Gaussian distribution, I highly recommend you to just watch some YouTube video about Gaussian distribution for 5 minutes, and you should be able to understand it. It's not within the scope of this course. This is your prerequisites. All right, so okay, Gaussian distribution. And we said that the assumption is that the standard deviation in different dimensions may vary. If you look at the chart here, this is 2 variables, so X and Y. If you think about our student example, this could be GPA, this could be first year salary after you graduate. And you know that their standard deviations are different because the size of your data set are different. We shouldn't call it size. What would be this number? The extent, right? This is minimum, this is maximum on the x-axis. This is minimum and maximum on the y-axis. They can be different. So the standard deviation in different dimensions may vary. They can be different, but these clusters needs to be axis aligned ellipses. Okay, so aligned like this, great, great, but it cannot be like this. So what's the implication of this? This means the correlation of your X and Y are not 0. Okay, every axis aligned ellipsis like this one and this one, the correlation between your 2 variables are 0. That means the 2 variables can be independent. They are not necessarily to be independent, but they can be independent. So this is a hard criteria for the data set. You can only have something like this, and each dimension has to be normally distributed. And in this example, it only shows you 2 dimensions, but you can actually have thousands of dimensions. That's okay for this approach. Okay, so assumption here, normally distributed for each component. Component 1, x, component 2, y. This is to explain the normally distribution to you. This is to tell you that standard deviation can vary. It doesn't have to be a circle, right? All right. So BFR algorithm is an efficient way to summarize clusters in memory so that we can process large data set for clustering very efficiently. And here we are requiring memory space in the scale of the number of clusters. This big O notation is your algorithm course. And we do not want it to be at the scale of your data points, right? So for example, you can have 1 billion data points and 1,000 clusters. And your memory consumption depends on the number of clusters you have, not the number of data points you have. This is very good, right? Even if you have lots of data set, you still have smaller number of clusters, and you'll be able to do this all in memory. Okay. All right. So BFR algorithm. Here's the algorithm. All the data points are read from disk, one main memory load at a time. So for example, if your data set is 100 gigabyte and your main memory has 20 gigabyte space for reading data and 12 gigabyte for processing, then every time you would read 20 gigabyte from this 100 gigabyte. Okay, and you use this part of the memory to help you process the 20 gigabyte data. So most points from the previous memory loads are summarized from some simple statistics. I will show you how. But to begin, from the initial load, we are going to select some initial k-centroid because we are running k-means-like algorithm. So we already know how many clusters we can have, right? So you have k clusters and k-centroid. So we can select for the first initial k-centroid by some sensible approach. For example, you can take k random points. You can take a small random sample from your 20 gigabyte and do the clustering. Use some clustering approach to cluster them optimally. Then you are going to have k-centroid. Or you can take a sample, pick a random point, and k minus 1 more point, each as far away from the previous selected points as possible, right? This is our previous approach when we talk about k-means. All right, so what does it mean then? Well, 100 gigabyte data, main memory 20 gigabyte plus 12 gigabyte. Okay, I'm just making this up as an example. So every time you read 20 gigabyte, so this is your entire data set. 1, 2, 3, 4, 5, right? Each of them is 20 gigabyte. 20. First load, you read this into memory and you run k-means, your algorithm lives here. You run k-means on this 20 gigabyte and you might be able to generate, let's say k equal to 3. 3 centroid optimally if you have enough memory space, if 12 gigabyte is enough. If 12 gigabyte is not enough for you to generate this based on our k-means algorithm, you can say, all right, let me just take some k random point, approach number 1. So then you have these 3 points. Or you take a small random sample, you say, all right, I don't want 20 gigabyte I don't want to run the k-means algorithm on the 20 gigabyte. I'll just take some sample, 2 gigabyte. And I run it, I have this 3 centroid. or you just pick samples like we used to do. Okay, so first step, you decided this 3 centroid. Now you haven't finished processing the first load yet. You still have 20 gigabyte, you still have some memory for calculation. So what do you do next? The next step is we are going to look at 3 different types of points in your first load, 20 gigabyte. So these 3 types of points are, the first one is discard set. This is called DS. So DS are the points that are close enough to a centroid so that we can summarize them. I remember now you have 3 initial centroid, but you still have all these points from your 20 gigabyte. So we are saying that the first one, if you are close enough to a centroid, like here or here or here, we are going to throw you away. We don't need you in the main memory. We are going to summarize you, okay? I haven't tell you how to summarize them. I haven't tell you what does it mean to be close enough. The second set is compressed set. So compressed set, called CS, these are groups of points that are close to each other, but they are not close to any existing centroid. For example, we might have something like this in your 20 gigabyte, still in the 20 gigabyte, right? This is your DS, this is your DS, this is your DS. But you have another group here, you have another group here. These are all close to each other, but they are not close to any of the centroid. So we are going to summarize these points as a cluster. We're going to summarize them, throw away the data points, but we are not going to assign them to any cluster. So what does it mean, summarize them? Remember in our previous k-means and other in the hierarchical clustering lecture, when we are summarizing a cluster, usually things are important, like the centroid and the extent of the cluster, right? So we are going to look at how we are going to summarize all this compression set. So John has a question. We are classifying the 20 gigabyte data to these 3 steps. Well, I won't call these 3 steps. We are classifying this 20 gigabyte data set into 3 types. You can have 1 step. Right. 3 types. Oh, sorry. Yes, you say types. My fault. All right. The last type of data points is the retained set. The retained set are the isolated points. They are not assigned to any compression set, not assigned to any DS. Maybe they're just here, far away from each other and far away from any of the clusters, right? So for these points, we are going to keep their information and we're not going to summarize them because we cannot. So let's look at one example. Say this is your centroid. For your first load, you have identified a centroid. Okay, there's another question for CS. How do you define not close enough? Very good question. I haven't talked about that yet. I will show you. So here, you just need to make sure that you understand these 3 different types of data. So you have the centroid, and you have all the data points within the, some close by areas of the centroid. These are your DS. You also have other data points that are close to each other. They all have a centroid, close to each other, have a centroid, and we say these are the CS because they are not close to any of the centroid for your DS. And you have your RS. These are the points that are far away from each other and also far away from any CS or far away from any of the DS. Okay, three types of data. And the reason why we can save memory is we are going to compress, or we are going to summarize the clusters here, here, and here, and here before we read the next load of 20 gigabyte. All right, so how do we summarize them? For each cluster, the discard set is summarized by the number of points, n, right? You are going to count how many points how many points you have in each of the clusters, so n point. I'm going to tell you why these are important, but just bear with me here. We are going to have a vector sum. In the vector sum, the ith component is the sum of the coordinates of the points in the ith dimension. For example, let's say your data is 2-dimension, you have y and you have x, okay? And here you have a point, 1, 1. You have another point. This is your centroid, but I just assume you have another point here, 2, 2. You have another point, 3, and 3. Okay, assume you only have these 3 points. So how do you write them? D1, D2, and D3. So D1, you have 1, 1. D2, you have 2, 2. D3, you have 3 and 3. Your n is what? Anyone would be able to answer this? What's your n? 3. Great. What would be your sum? Your sum is a vector. So your sum is a vector for how long? Ith component is the sum of the coordinate of the point in the ith dimension. Okay, so the length of the sum is the length of your dimension. Okay, so 2-dimension. Look at x. What is the sum in the x dimension? So Dinley said 6, 6. Great, that's the answer. Right, so 1 plus 2 plus 3, 6 for your x dimension. 1 plus 2 plus 3, you have 6. This is for your y dimension. Cool. Sum vector. What would be your sum square vector? The ith component in the sum square vector is the sum of the squares of the coordinates in the ith dimension. So what would be the sum of squares for x? 1 plus 4 plus 9, 14. Great. And 14. Okay, cool. Once you generate these summary statistics, you can throw away all the data set here. So we are going to throw away this. Okay, so think about this. If each coordinate is 4 byte, this is 8 byte, 8 byte, 8 byte. Originally, you need how many bytes to store the 3 data points? 24 bytes. And now you have n equal to 3. You have to store this. So 4 byte. You have to store this. 4, 4, 4, 4. So 16. So 4 plus 16. Now you are using 20 byte. Okay. Originally, with the raw data, you are storing your data with 24 byte. Pretty cool, right? One thing that's really awesome about this approach is this doesn't change. No matter how many points you have in this cluster, you always need 20 byte. Okay, because the number of points require you 4 bytes, and the size of these two vectors are fixed. So you always need 1, 2, 3, 4, 5. 5 times 4, each one assume 4 byte, you need 20 byte. But this one, the first one, depends on the number of data points in the cluster, right? We only have 3 points, so it's 24 byte. What about if we have 3K points? Well, that will be 24K bytes, right? So this is what we mean. The memory consumption is based on the number of clusters, not the number of data points. All right, so these are 3 things you have to store. And why do we have to store them? Well, number of points might be obvious, but why do we want to store sum and sum square? Let's just look at how you calculate variance. And again, you should already know this, but for the completeness of this course, let's just look at how you calculate the variance of a data set. The variance of a data set is the expected number of a data point minus the expectation of a data point. This is the average of the data point and the square here. Okay. If you take this apart, x minus ex squared becomes x squared minus 2x ex plus ex squared. So how do we do this? Well, you can take x2 out, right? Becomes the expectation of x2. Great. How about this? If you take this out with the expectation of x is expectation of x. The expectation of x is the expectation of x. And here's the same, right? So now you have e, the expectation of x squared minus the expectation of x and square, right? Because the variation is written like this. And this is the expectation or the mean of x. All right, if the variation can be rewritten as this, so remember what have we stored in our on the previous slides? You stored n, you store sum, and you store sum square, right? So you have sum here, you have sum square here that you can use to calculate the variance. Let's look at here. So when we are summarizing all these points, we need 2d plus 1 values to represent any size of clusters, right? 2d is the number of dimensions, and we need 2d because the first d is going to be used to store your sum vector. The second d plus d, the second d is going to be used to store your sum square. And this plus 1 is the number of data points, that's the n. So based on all these values we have stored about a cluster, we can calculate the average in each dimension, which will be your centroid, right? How do you calculate the average in each dimension? You just take the sum in each dimension and divide it by n. So that's here. All right, so what would be the centroid? You take the sum, 1 plus 2 plus 3, it's 6. 6 divided by 3, you have 2. 6 divided by 3, you have 2. So you have centroid 2 and 2, right? So based on your statistics, summary statistics, you can calculate the centroid. Good. That's here. You can also calculate the variance by taking your sum square divided by n minus sum divided by n and square, right? Then you take you can take the square root of this variance, then you have a standard deviation. Okay, so if you look at this, this is every dimension you can do this. This means just take the statistics, you are able to estimate the Gaussian parameters for each dimensions. You have the mu and you have the standard deviation. The mu is the centroid. The standard deviation is calculated like this. So with this, how do we really do the clustering? Well, first, you process the memory load of points. You find the points that are sufficiently close to the cluster centroid and add them to the cluster and the DS. Okay, I haven't told you this yet. Sufficiently close, but we are going to look at this. These points are so close to the centroid, so we can summarize them and we can just discard them. So these are your DS. Once you do that, you use any memory clustering algorithms to cluster the remaining points in the retent set from the last run. And if you can find clusters, the clusters will go to the CS, outlying points will go to the RS. Okay. The second part, with your DS set, you're going to adjust the statistics of the cluster because now you assign more points to the DS. So you have to update the sum, update the number of points in the cluster, and update the sum square. You are going to consider merge compress set if they are close enough, and we're going to talk about close enough. If this is the last round, you're going to merge all the compressed set in the CS and all the RS into the nearest cluster, and you are done. So again, it looks like this. All right, so how do we decide if a point is close enough to a cluster so that we want to add it to the cluster, right? This could be adding it to the DS set or adding a point to a CS set. The second question is, how do we decide whether two compressed sets, the CS set, to be merged together? So define this sufficiently close. Your Gaussian distribution, you have all these properties of your Gaussian distribution. We know that 68% of points will be one standard deviation away from the mean, 95% of the points are two standard deviation, and so on. So to figure out sufficiently close, we have two ways. First, we can use the Mahalanobis distance with a threshold. And we're going to look at Mahalanobis distance on the next slide. High likelihood of the points belonging to the currently nearest centroid. This is what Mahalanobis distance will tell you. So let's look at it. This is your Mahalanobis distance. This is a normalized Euclidean distance from the centroid. So why do we call it normalized? If you look at here, first you take your data point X, you subtract it by the centroid of a cluster, then you divide it by the standard deviation of that dimension, and you take square, and you do sum of a square, and you take the square root. Okay, so in general, for all the points, for a point in this D dimension and one centroid in this D dimension, we want to be able to calculate their distance, right? Remember, we talk about Euclidean distance, we talk about cosine similarity, we talk about many different types of distance. But this time, the distance that we are going to use will consider the distribution of the data in each dimension. That's your standard deviation. So first, you are going to normalize your data. This is actually standardize your data because you are going to divide it by the sigma. You're going to take the sum of the square, take the square root, and you're going to have your distance. One thing that's very cool about this is, think about this. In what case you are going to have a square root of D? In what case you are going to have a square root of D? All right, sounds good. When this gives you 1, right? That means in every dimension, your data points are one standard deviation away from the centroid. One standard deviation away. And that has to be for every dimension. So you have a square root of d. So this is very cool then. If we know this, we are able to have some informed way to generate a threshold for this Mahalanobis distance. So if clusters are normally distributed in these d dimensions, which is the case in our algorithm because we assume this, then after our transformation, the way we calculate the Mahalanobis distance, one standard deviation away from a centroid means square root d away from the centroid. And we know that 68% of the points of the cluster will have a Mahalanobis distance smaller than 1 square root of d. Right, that's here. 68%. So one thing that we can do is we can, based on, let's say this is your cluster, you have a centroid. Now you want to decide if you want to add this point to the cluster. You can say if this point is one standard deviation away or 2 standard deviation away from the centroid, then we are going to accept it. So for example, you can say accept the point for a cluster if the Mahalanobis distance between the point and the cluster center is smaller than some threshold, could be 2 standard deviation away, right? 2 standard deviation away means you care about 95% of the points, so it's probably somewhere here. If you want your cluster to be very compact, you just take 1 standard deviation, which is okay as well. So if we look at Mahalanobis distance and compare it with your Euclidean distance, it looks like this. So say this one is a uniformly distributed points. Your Euclidean distance works well, right? Every circle, each buffer has a circle, and every circle indicates a distance from the center point here. But here you have normally distributed points. Euclidean distance doesn't really work very well, right? Because this point set are more dispersed in the x dimension than the y dimension. So your Euclidean distance still doesn't care and draws circles everywhere and consider each axis or each variables in the same way. Your Mahalanobis distance, working on normally distributed point, remember when we calculate the Mahalanobis distance, we are going to divide the distance measurement x minus c divided by the standard deviation in each dimension. So it naturally gives you something like this to measure, right? So pretty cool. You'll be able to tell you the distance from a point to the centroid and also consider the variation in each dimension. All right. So that's your Mahalanobis distance and how you would be able to use it to decide if a point is close enough to a cluster. So the next question is, how do we combine 2 clusters? Well, when we think about combining 2 CS clusters, we can compute the variance of the combined cluster, right? Because we already have n, sum, and sum square for all the CS. After we combine them, we can calculate the variance. And if the variance is below some threshold, we can combine them. If it's larger than some threshold, we don't want to combine them. Or there are also many alternatives. You can treat dimensions differently. You can say, I want to focus on the first dimension because I think it's very important. Or you can consider the density. For example, if you merge these two, the density is not great because you don't have any points, right? We talk about similar methods when we were in our hierarchical clustering lecture. All right, so that's everything I want to tell you about the BFR algorithm. I will summarize this again after the break. I just want to run the entire algorithm to you, show you how to run the entire algorithm from the first node to the clustering result. Let us take a 10 minutes break, come back at 7 p.m. If you have any questions, feel free to post it in the chat. Hello, people. I'm back. All right, I'm going to show you the BFR algorithm, which you are going to implement for your assignment 5. How many of you have finished your assignment 4? No one? All right, so BFR algorithm. There's many tricks in this algorithm because it's actually very flexible. So let's say you have 100 gigabyte and your memory space is 20 gigabyte plus, let's say 12 gigabyte you want to use for algorithms. Okay, this is for data. And you slice it into 5 pieces because each time you can only read in 20 gigabyte. All right, first round. First round is a bit tricky. First round, we read this. Assuming we are going to have 3 clusters, k equal to 3. So these are all your data points. Okay, a couple ways you can do this. For your first round, let's just talk about 2 ways. First, you can randomly pick one cluster center, then pick another one far away as possible, and the third one far away as possible, right? Like we talked about before. Then you are going to assign all these other points here, here, here to some of the clusters. Okay, the difference between this and the k-means is you're going to assign this to this cluster because it's closer. However, you do have some threshold, distance threshold, to say, all right, this point is too far away, I don't want it. So eventually your cluster might look like just like this. So one thing that's very important to know is we are working on Euclidean distance. And since you randomly pick data points, you do not have sigma, right? You only have the cluster center. So you cannot do Moharanobi's distance. You can only compare each point to the cluster center and decide if you want to assign it to the cluster. Assuming you do this, you probably have 3 clusters like this. What about the others? Well, the others, you run a k-means algorithm again on all the other points. Here, here, and here. The trick is that you run a k-means algorithm with a large K, because now your goal is to identify the compressed set. You don't know how many compressed set you have. So let's say we run a k-mean with k equal to 10. You are going to probably find 1 cluster here, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. And when you do this, it's actually very cool because now you have all these data points. You have all these clusters with only 1 point, and these are your RS. Because they only have 1 point, they are not close to anybody else. These are your RS. This is your CS, 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 DS, DS, and DS. All right, very good. So great. Now you are done for your first load of the data points. Second step. Now you are going to throw away all the points. So here, I'm not going to have this point. I'm not going to have all these points. This is not a centroid anymore because I now assign new points. And points, no points, no points. All right, because we are working on a two-dimensional data set, 2D here. So we are going to have two. Well, we are going to use D plus 1 to store every compressed and DS clusters, right? So D equal to 2. So we're going to have 5 component. So 5, 5, and you get the idea. So how many do we have? We have one, oh, sorry, not a C, not the RS1. The RS1, we still keep the original point. So how many compressed and DS do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11. So we have 11 times 5 components, assuming each component is 4 bytes. So we have what? 220 bytes. So why is this important? Because next run, you're going to read in 20 gigabyte again, but then you are going to have some storage for this. But compared to this 20 gigabyte, this is so tiny, you don't really account for it. So we might just say, now here we have 12 gigabyte minus 220 byte that we can use for clustering. Okay, good. So now you are reading the second data point, and let me just put the second data point somewhere randomly. Let's say this is your second data point. So second memory load of data points. So what do you do now? Well, for each of the data point, you are going to calculate Mahalanobis distance, because now you can use Mahalanobis distance. Each centroid is not a centroid anymore. Each centroid actually represents a cluster with the standard deviation and mean in each dimension, right? Standard deviation tell you the extent, mean tell you the location of this, right? So standard deviation, standard deviation, standard deviation, standard deviation, and so on. So you test the distance between a point to a cluster, use the Mahalanobis distance. You say, okay, great. Now for this new, I'll just use red. For after I calculate the distance from each data point to a DS, the DS becomes larger, right? Because now it contains more points. Nearby points, nearby points, and so on. Then you can also test the remaining data points, say here. This one is not close to any DS, but it might close to a CS, like here, right? So this is your new CS for this one, new CS, and new CS, and new CS, and new CS. Okay, awesome. Next step is you're going to look at nearby CS, and you're going to say, all right, how about I combine them? If I combine them, do I have a large variation in any of the dimension? If not, I would just combine them. So eventually you might have something like this. Which color should I use? Purple. So this is one CS. This becomes one CS. This is the CS, but with new data points. This is another CS, and this is a CS. Okay. And what about the other points? Well, the other points are still your RS, because they are not close to any CS, they are not close to any DS, and you are done. Once you're done, you're going to update this 5 component to D plus 1 component to summarize each of the cluster, the DS and the CS, and you are going to remove all the data points. You remove all the data points so that you have the memory space to read in more data for clustering. Something like this and like this. Cool. And you keep doing this until you read the entire file. Okay, let's say you read the entire file, you do this, you did all this, and this is your final result. But because this is your last round, so what you want to do is you want to say, all right, because my goal is to have 3 clusters, I'm going to combine the CS and the RS into the nearby DS. So your result looks like this. Here you have 1 cluster, here you have another cluster, and here you have another cluster. You have 3 clusters. So there is a question, do we need to test all the rest of the points? Isn't that expensive?
Well, I mean, after completing the CS, you said you want to pick a point outside the CS and test if it should be included in the existing CS.
Yeah, you have to do that for every point. If you don't do that, you don't know if you need to keep that point in the RS or if you want to summarize it, right? So it's expensive. K-means is expensive anyway. This is expensive, but this process help you to process large data set without reading the data and writing the result back to the disk and read the data again. So you can do this iteratively to handle large data set.
But why don't we just keep the CS and let the rest of them go to RS?
Then you are going to have too many RS, and eventually, remember here, this is very small because this is the data, this is the memory space you need to summarize all your CS and DS. Oh, I forgot to plus. We need to still store 2 RS, right? Remember at the beginning, these 2 cannot be clustered anywhere. You have to store their original data. So if you have too many RS, that means your memory space is going to be occupied by all the original data that cannot be classified or assigned to any cluster, any DS or CS. And eventually you are not going to have 12 giga for your algorithm. You are not going to have 20 giga for your data. This will be very tiny because it's occupied by the RS.
So you're saying we should include as many points as possible to the CS so that we can leave as less RS point as possible as outliers?
That's correct.
Okay,
But
thank you.
but you don't. But your goal is not to add RS to the CS, because if an RS is far away from your CS, you don't want to add them, right? So it really depends on your data. But if you have enough CS, it's usually okay. But the trick here is you use a large K to find all the CS. You cannot control how many RS you will have, because if you say or an RS that's far away from a CS still need to be assigned to a CS, then your CS cluster got really large and the variation will be very large, right? So you don't want to do that. For example, let's say this is your DS, this is your CS, this is your CS, this is your DS, and you have all other points here, right? Remember we said that you can, because you have a summary statistics of all these clusters, you can do Mahalanobis distance and you compare this point in the Mahalanobis distance to this cluster. And if our goal is to assign as many RS as possible to the CS, that means we can just grow your CS to be like this. But that's not very nice, right? Because this cluster becomes very large and these two are outliers. You don't have any data points here. So you still want to use a nice Mahalanobis distance threshold, like I think on the slides we said 2D. 2D is a nice one because it will cover 99.5% of the data if you assume it's a Gaussian distribution in each dimension. Okay. So your goal is not to assign as many RS to the CS. Your goal is to be able to summarize as many clusters as possible based on your definition of a cluster, like that Mahalanobis distance threshold. All right, any more questions? If we don't have any questions, I think we can just go ahead for our quiz today. So please go to the Blackboard. Under quiz. You should be able to see quiz 9 due at 8 p.m. The due time is always on Blackboard. So if you click on the quiz 9, you should see the due time. It's 8 p.m. Please turn on your camera. And let me just briefly talk about the quiz today. For your quiz question number 1, explain how AGM works to find communities in a graph. You can use an example. You don't have to, but use an example, it's easier. You have to explain how and why the MLE process needs to be repeated to find the optimal solution. Well, we know that AGM, there's no way we will be able to find the global optimum, right? But you have to explain how MLE is used in this case. And I list all the steps here to help you, just in case you don't remember. But I think this is important that you understand. All right, specifically, you have to explain and show the AGM model and the parameters. You have to explain all the parameters in AGM, explain how you can use the AGM model and the graph to generate the target likelihood function. Remember our 1, 2, 3 steps. Third, how you will be able to optimize the likelihood function. How are you going to find the parameters that will be able to optimize the likelihood function? And 4, once you find the parameters to optimize the likelihood function, what are the next steps? The next question is to explain how BigClam works compared to AGM. So now if you already explained AGM, this one becomes easier, right? So in BigClam, I show you already on the quiz the probability function, but you have to write out the BigClam target function in this case. That's the write your answer using FU and FV. Then once you are able to write that, you need to explain how you are going to use membership metrics in the gradient update process to find the optimal solution. And here I want you to explain how you would initialize these membership metrics. We talk about this in class, and I told you to read the paper, look at that part in the paper. The third question is hierarchical clustering methods. Explain it and show the computational complexity. This one is super easy. The last one is also pretty easy. You just explain curse of dimensionality, what is it, and why do we have this problem? Why is it a problem? Right? Okay. All right. Good luck.
Guys, time's up, and I'll end the session.